Alternators are the workhorse of the power generation industry. It is capable to generate AC power at a specified frequency. It is also called a synchronous generator. Electricity is produced in alternators by electromagnetic induction. To generate electricity in a coil, either the coil should rotate with respect to magnetic field, or a magnetic field should rotate with respect to the coil. In the case of alternator, the latter approach is used. Rotor and armature coils are the two main parts of an alternator. Rotor produces a rotating magnetic flux. Armature coils are stationary, and rotating magnetic flux associated with the rotor induces electricity in the armature coils. This kind of rotor, shown here, is known as salient pole rotor. For gaining better insight of its working, let's consider a rotor with just 4 poles. Rotor coils are excited with a DC power source. Magnetic field produced around it would be as shown. The rotor is made to rotate by a prime mover. This makes the rotor flux also rotate along with it, at the same speed. Such revolving magnetic flux now intersects armature coils, which is fitted around the rotor. This will generate an alternating EMF across the winding. Here is a slowed-down version of rotor-stator interaction. For this 4-pole system, when the rotor turns half revolution, induced EMF takes 1 complete cycle. It can be easily established that frequency of induced EMF, rotor speed, and number of poles are connected through following relationship. It is clear that frequency of electricity produced is synchronized with mechanical rotational speed. For producing 3-phase AC current, 2 more such armature coils, which are in 120-degree phase difference with the first, is put into the stator winding. Generally, one end of these 3 coils are star-connected, and 3-phase electricity is drawn from the other ends. It is clear from this equation that in order to produce 60 Hz electricity, a 4-pole rotor should run at following RPM. Such huge RPM will induce a tremendous centrifugal force on poles of the rotor, and it may fail mechanically over time. So salient pole rotors are generally having 10 to 20 poles, which demands lower RPM. Or salient pole rotors are used when the prime mover rotates at relatively lower RPM. Pole core is used to effectively transfer magnetic flux, and they are made with fairly thick steel lamina. Such insulated lamina reduces energy loss due to eddy current formation. Armature winding of 3-phase, 12-pole system is shown here. A stator core is used to enhance magnetic flux transfer. DC current is supplied to rotor via a pair of slip rings. DC current is supplied either from an external source or from a small DC generator which is fitted on the same prime mover. Such alternators are called self-excited. With variation of load, generator terminal output voltage will vary. It is desired to keep the terminal voltage in a specified limit. An automatic voltage regulator helps in achieving this. Voltage regulation can be easily achieved by controlling the field current. If terminal voltage is below the desired limit, AVR increases the field current, thus the field strength, This will result in increase in terminal voltage. If terminal voltage is high, the reverse is done.
Hello friends, in this video we will see the procedure of external excitation to main alternator, also called as flashing the exciter field. One of the most common problem in generators is no voltage buildup due to loss of residual magnetism. Residual magnetism in the generator exciter field allows the generator to build up voltage during startup. This magnetism is sometimes lost due to long storage prior to use or without use, reversal of the exciter stator magnetic field while flashing with a battery, or rewind of the exciter stator. Restoring this residual magnetism is possible and is sometimes referred to as flashing the exciter field using 12-volt battery as shown in image, and we will explain in this video in detail. We will demonstrate the alternator excitation procedure on Stamford P series alternator, which is fitted with AVR AS480. To start the alternator excitation procedure, open the AVR cover fitted at rear end of alternator to get the access to alternator AVR. After removing AVR cover, locate the exciter field leads F1 and F2 as shown in image. You can also refer the diagram provided at backside of AVR cover. Exciter lead F1 is positive, generally it is red color, and F2 is negative, which is gray in color. If you see exciter lead closely, you will notice that F1 and F2 is written on cable. You can see in video F1 and F2 is clearly visible. After locating F1 and F2 leads, remove both F1 and F2 leads from AVR carefully. Now we need to connect 12-volt battery to these leads. Take electrical cable and connect lead F1 to the positive pole of battery, while F2 to the negative pole of the battery. Ensure that while doing this exercise your generator is at rest condition. You can see your battery voltage is 12 volt and positive and negative is connected to F1 and F2. Give battery supply for about 5 to 10 seconds and remove the connections carefully. After removing battery supply, reconnect F1 and F2 to the AVR and start the generator and measure the voltage. Now the alternator should develop the rated voltage.